Okay, Monday. Let's keep going. I'm gonna do electromagnetism and then linear algebra. So let's continue from the last chapter or subchapter, which was 2.4, and it was continuous distribution of charges. So I talked about different way to view charges. So if you have the charge Q over some volume element, let's just draw a small drawing here. So let's say I had this was my coordinate here. Then we had some figure, right? Some volume figure. Then it has some kind of d volume, just like that. And then, of course, I have my vector. I should have another call a vector up to there. That's just r. And we can write that charge Q, which is continuously distributed over this volume here, as just V. And then, of course, V, and then, of course, rho V as a function of R, right? Because R points where that D volume is. And, of course, that is where we are looking at the density. And that's just Q. And, of course, you could state also that the density is just Q divided by the volume, which is just coulombs. You do it like this, just coulombs over meters cubed. And all of this was a bit motivated by this notation here. We are integrating over all the charges, dq, right? We can also write this as for a surface. So I can draw just those pretty quick, those two last situations, which was a surface, right? Just like that. We have a small element, ds, right? We have a vector up there pointing to ds. And also what we have is a line, a small line segment, dl, just like that. And then, of course, we have a vector up there, again, r. And of course, both of these can be written. I can, of course, write. It wasn't ds or dl as a vector. No, of course not. Why did I do that? I'm so used to the surface integrals. This ds and dl, they should be vectors. That doesn't make any sense. I just had to check, just to be certain. I'm going to be mad if they were vectors. No, they're not vectors, right? And you're not vector, right? Okay. I'm like, what have I done? Of course, and then I can write Q in terms of that surface as rho L. Then, of course, dl. And rho L should be, of course, be a function of R. Sometimes rho L is actually written as sigma. And if you have a line charge over some kind of curve or a line, then you say that I said rho L there, I meant rho S. And rho L is sometimes written as lambda in some textbooks. Why was I so for DL? It's DS and no vectors. God. Okay, so that's the two other ways, of course, we can write the charge here, right? For if the whole surface or the whole line had a continuous charge distribution. Okay, and of course, this is going to motivate the electric field, right? So if I want to know the electric field, right, of R, that is the same as the integral over Q, then of course dq over that 4 pi epsilon 0. Then I have, let's say, r hat over r squared. Just write it like this. This can also be written as the integral over a volume. So let's say we wanted, I'm going to draw the image. So let's say that we had, let's say we had some kind of object here. Again, I don't know why physics is so Why is it so obsessed with this figure? It's always this figure. The volume. And then let's move this coordinate system so we can create an electric field. So, and then let's say this is my observation point, right? So that's, or I can move it a little bit. So my observation point is here, which means my R vector is pointing there, right? That's my observation point. And like we did earlier, we imagine that there's some small test charge there, right? Approaching 0. So we have an electric field. Then, of course, I need a vector pointing because I need density for the volume. And that's R prime. That's important. And then, of course, we have that relative vector because we have to point where the electric field is affecting our position, right? And that's, of course, that relative vector R. Now, this can, of course, be written prettier than we did up there. We can write this as a volume. And then, instead, we can say rho. And rho is over the volume. So rho sub volume. And then it's going to be actually in terms of R prime. Because remember that R prime points to our integral, and that, not our integral, I mean our figure here, right? So we are actually only going to integrate over the figure, which is actually over just R prime. We are not actually integrating over our position, right? So actually our position is just a constant there in this integral. But we are viewing the electric field in terms of our position. So the electric field is a function of our position. All right, 4 pi epsilon 0. And then we can write r, the relative vector r, minus r prime, divided by r minus, of course, r prime. And this is cubed, right? And we need, of course, the volume. Did I remember? I dq there. And just to make it very clear that we are integrating over r prime, because that belongs to the object, we are also adding prime to the volume, just like that. Okay, so now what we should do is an example in order to, and this is of course true for line integral or surface integral, etc. Okay, if you want the electric field there too. Okay, so now let's do an example. So we have some kind of uniformly charged disk. Oh no, not disk. That's the next. A ring. So we have some uniformly charged ring. So this blue segment here is uniformly charged. So the total charge is Q, right? And the radius here is just A. We can say that there's some phi here. Polar coordinates make sense. And then our observation point Z is there. So it's at Z and of course Z hat. Just like that. And then we want to know how this charge is affecting us. So if it was some small test charge, how would this field here, how would that be affecting us? We can write that in terms of an integral, and it's smart to just start with this dq, just to make things clear. Epsilon 0, we can go with, I don't want to use r hat, so I use r over r cubed, right? Then we can do some clever things here, because I know rho L, since it's uniformly charged, rho L is just Q divided by the total length. That's just Q divided by 2 pi A, right? Okay, we're going to need that later. We can rewrite our integral volume, and that's just rho L. And rho L is just constant, right? So we can just, there's no function there. We still have 4 pi epsilon 0. And then r, that's just r minus r prime. And then r minus r prime. And then, of course, cubed. Then we have dl. Just like that. Then remember that r, that's just 0, 0, z. And r prime, of course, that's just polar coordinates, so we're going to use a cosine of phi, a sine of phi, and of course just 0. Which means that the relative vector r, capital R, which is just r minus r prime, is actually just minus a cosine of phi minus a sine of phi, then of course z, just like that. Then that integral there, that was a nice arrow, volume. Then I can, of course, let's move out rho L 4 pi epsilon 0. We're integrating now in polar coordinates. That's 0. That's 2 pi. And then we have r minus, that's just minus a cosine of phi minus a sine of phi. Then we have z. And then we are dividing by, if you, of course, that's a squared, this squared, 1, z squared. So what we have is just a squared plus z squared. And then, of course, this is 3 over 2. And, of course, we have to, of course, it's like a linear transformation, but we are going from Cartesian to polar. And that's, of course, you have to compensate with the radius and d phi. That's just d phi, and then we can put a there just to make things more neat. Okay. Now, the only thing that goes in the d phi, the only thing that actually contributes here is z, right? There's going to be no in x or y, right? So we just have z there. So what we can do is just say a rho L 4 pi epsilon 0, 0 to 2 pi. Then we just have z in the z hat direction, right? That should be all right. That's just z in the z hat direction, and divided by a squared plus z squared, 3 over 2, and then d phi. Then we just get 2 pi, so the whole of this is just 2 pi a rho L 4 pi epsilon. My handwriting just gets worse and worse. Z divided by a squared plus z squared, and of course this should go in the z hat direction. Remember that all of this is just q, right? That should be, I think that should be correct, shouldn't it? What did we write? Q. So 2 pi a multiplied by rho L, that's q, right? So this is just q divided by 4 pi epsilon 0, pretty neat. You have z, a squared, z squared, 3 over 2, z hat. And that's correct. And if we now, just to test our case, let's say that we took the limit and we put z to infinity, what would happen then? Then, of course, what we would get is q over 4 pi epsilon 0. We get z, and we just get z divided by z squared. That's just 3 over 2, so that's just z cubed z hat, which is actually, yeah, we can just write it like this, z hat. Or I can do it like this. Perfect. And this is, of course, exactly what we would expect, right? If I moved as high as possible over that ring, I would view that ring as just one point charge. And this is exactly that. Perfect. If you're a bit clever, you can, of course, realize that this is, of course, just brute force. You could have done this much more cleanly. Why? Because you can instantly see that if I draw a vector from here and I drew a vector from here. This and this, if I made a component, I would have this guy in this direction and this guy in this direction, which means that the only one contributing is in the Z direction. So you could just entirely ignore X and Y. So if you were a little bit clever, you could start off like this, saying Ez is just the integral over, again, that volume, and then you would just start immediately at Z, right? So you could do that instead, right? So that's also a clean way of doing this, but this is all right for now. Yeah. Let's see. I haven't tried to code this, not a lot, so I can just see if I can try and make this work from scratch. We'll just try and see how it goes. Let's see. Maybe I try it with. I need some work in with Jupyter Notebooks. Let's just try it. So test.ipnb. Okay, I don't want to stay in the Jupyter Notebook here, right? Okay, you can just stay there, but what I want is, of course, here. So let's just move to this test file. Let's add one code. Okay, so import matplotlib. I don't want all this nonsense here. Matplotlib dot pplot as plt, and then import numpy as np. Then import. I think I need scipy. Yeah, and the scipy dot constants. Was it that constants as sc? That should be all right. Yeah, it's always so slow with this stupid kernel. Now it was fast. Nice. Okay, perfect. We had a as just 1.0, right? And then n, because now what we want to do, we have to do this numerically, which means that we will take that same guy and we'll chop him into n pieces, right? So we will have n pieces. You could say that q would be equal to n and then multiply by the q, like that. That will be our idea, right? Okay, so that's the idea for now. Let's see, so n, let's keep it at 20. That makes sense. We can just keep those constants there, that's all right. Okay, and what do I want? I want this function. So the electric field, we need our position, right? That's, we call that r, and r prime, we can call it r sub I, and then I want q sub I as well, right? Okay, we have r, then of course r is just r minus ri, and then we could say r norm is just equal to, I found this, that was better, r norm is equal to np.linearalgebra.normalize, and then r. Nice. Okay, then we just want to return each piece, right? Because now instead of the integral, we are summing over all of those small pieces of electric field. That sounds stupid, but that is what we're doing. Okay, and that's just, of course, 1 divided by 4 pi np dot pi multiplied by sc dot epsilon 0, right? That's what we have, and we are going to multiply by, of course, r, and then divide by r norm cubed. That's one piece, but I also need rho here, don't I? I need rho. This is just that guy, but I need rho, don't I? dl, so that's e. I think I need rho, because this is just 1. Let's see, let's go back. So what we have now is that the electric field is the sum of I, and I need Q of I. So each piece, right? So I would have need Q of I. I need 4 pi. Oh, I have Q of I, of course. Yeah, that's foolish of me. I knew it was something, right? So if we go back here, Qi is what I want there. Yes, perfect. This should be all right. Yes. Okay, that's all right. Now we want two lists. I want the R position and the Q position, right? So I want R list, just an empty list, and then Q list as well. And then I want to loop through. So I need to go for I in range. And then what do I want? What's the range? Of course, that n, which is 20. I need to specify what R is. Let's see. Of course, we can state that R here is equal to numpy dot array. It should be 3 coordinates. It should be, of course, that's one specific R. That's not our R. Our R is just set. Yeah, I want Ri. I'll call this Ri. Yes, Ri. Just like that. Yeah. So I have A times cosine. Cosine. I need phi as well. Yeah. We need to make. Let's see. So phi. Let's see. So phi or d phi. D phi is just 2 pi divided by n, isn't it? Yeah. Or I d phi, that particular. That's just I. I d phi is 2 pi. No, d phi is just 2 pi n. And then I need I d phi. That's what I need, right? In order to cover the whole thing. And that's from I equal to 0 up to, of course, n minus 1. That should be correct, shouldn't it? So I go all the way around. I think that should be correct, shouldn't it? So we can say d phi. What did I say? There's just 2. It's the same everywhere. So it's 2 times np dot pi divided by the total, right? So then we can just use I here to loop over that. So we can say that phi sub I phi sub I is just equal to I times d phi. Yeah, that should be very much correct. So phi sub I, that sounds stupid, but that is how it goes. That's just np dot sine and of course phi I. And I want you also to be np dot cosine, of course, and there's no set there. Right, this should be pretty good. Cool. Okay, then we can say that our list dot append, and we can just append R sub I, and we also want the same as Q, so d Q. I actually want d phi like that. That's better. That makes more sense. So dq is just q divided by n, of course. So we can just say that q list just append dq. Do I want dq? Yeah, just dq, dq, dq. Right. Do I want dq times I? No, that wouldn't make sense, or would it? Do I just want dq? Or do I want dq times I? It's the same charge. I'm going to put just dq. Yeah, so it's just dq. Okay, that should be very much all right. We can just... No, it wasn't all right. What was my mistake? Name q is not defined. Oh, we need some charge for q. Let's go to our constants and just call q, and that should be equal to 1. Yeah. Now this can be non-complaining. We go below, and now we can do that mesh grid approach. So let's say Lx, Ly, Nx. Now let's call it Lz. And then we have Nx and Y. That should be equal to, let's go with 3, then 3, of course. And then what we had 20, so 41, 41. That should be pretty neat. And then we can go and say that x is equal to np dot linspace minus lx, and then we have lx, so length x, and then nx. Right, set is of course just there you go, and there you go. Right. No, I wrote ny. There you go as well. Okay. Then we say Rx, Rz is equal to np dot mesh grid, and the mesh grid should of course be x and y, and always remember that indexing. Okay, we run this, it wasn't happy. What did I do wrong? Indexing ij. What? Name y. Oh, yeah, of course. Set. Confusing. Okay. That's all right. Let's write a new cell. So I can just say for I in range, and then we have nx, then for k in range and z. Then we could say that our r vector is equal to np dot array, and then we have the first coordinate is rx ij, the second coordinate is 0, and then we have r, y, and then I comma j. That should work, shouldn't it? We're skipping y because this will just be a plane, and this will be exactly the same for y. That's why you will see it in the graph. Okay. Now this is all right. Then we can say for, we need to run through all those charges. So for, he used IC, that's for the it charged, I think. In range, we can run len and qlist. Yeah, we can do that. Okay. Now this is where the tricky part comes. Let's see, we could say ex, ey, ez is equal to let's see, it's equal to our position. It should be our position, which is r. R should be our position. Yeah, the field is equal to where we are, shouldn't it? No. Oh, it's something I'm missing. No, it should be equal to what we have and the new one. Yeah, of course, I'm a moron. So ex, and I'll also forget that ex, I comma j, ey, I comma j, and I of course forget those. No. Yeah, let's run I comma k, ik, and I should have, yeah, maybe I should have done that instead. And just say that ey is some kind of dummy variable here. Ey, and of course this is just k. This is also k, right? And I should have ex is equal to rx dot copy, and we should also say ey e z 0 rz dot copy. That should work now. It should stop complaining. That should be equal to should that be equal to either it's plus equal, or oh, it's at that position, or it's just the coordinate. right? I think it's plus something. Yeah, let's just run with. Yeah, let's just run with D, one of them, right? But maybe it should be plus, shouldn't it? Oh, yeah, maybe. Maybe I should just write plus equal. No. Okay, let's try and run that. That it would have made sense if that was correct. Like this, 0. It should be all of this, and then plus, of course, the new one, which is just E, and that's just R. That's just R. But E, X, Y, Z. Wait, why can't I just, why documentation R, then I need RI, R sub I, that's of course, or R list, and then of course IC, and then I need the last one, which is QI, there's Q list, and then IC. Oh, I don't know if this is correct. Yeah, okay, yeah. Let's see. It's either that plus or it's nothing at all. Let's see. Yeah, there was some funny business here. Name RY is not defined. What did I say? RY? Oh, RZ was what I meant. Yeah, there's more nonsense here. Name RI. Okay. Yeah. Of course, there's no RI. Why didn't you state that earlier? Yes. Okay. Still value error. Yeah, I think this is not correct. Maybe it should be setting an array element. But maybe I should have written this as an array. That also feels very weird. Why would I do that? I have what we already have plus, okay. It would have made sense. Let's see. No. No. Why did you do that? I didn't mean that. Like that. Has no attribute. IK, EZ plus E. No. Okay, let's see if this then works. Was it that was my problem? Yeah, okay, maybe it is that. Okay, let's see if this will work. I'm curious. We have, of course, it will be mesh grid, so it's just plt.mesh, or is it np? Oh, it's not np, it has to be plt.mesh grid. Where haven't I? What is happening? Where is mesh grid? As plt, are you so slow? plt, should that be correct? It's numpy.meshgrid, plt.meshgrid x, y, and of course, no, not x, rx, rz, then ex, ez. No, it's not mesh. Oh, is it numpy? What is going on? Yeah, it's numpy. Mesh grid. What? What am I doing? There's something that's missing here. Okay, I'm going to check that. I've used this a million times. Why? What am I doing? PLT dot. Ah, you moron! I knew it was something. Dot quiver. Why did I think mesh grid? I also know it was a graph for some reason. Yeah, that should be it. Yes, very good. This is not correct. I'm close. It's this line here where I missed. But this looks kind of correct, actually, in my opinion. Shouldn't it? That's not bad. let's just try and tighten this up. plt.axis equal. Yeah, it's not bad actually. Yeah, it's actually pretty good, but I don't want this from here. It should actually be like 2 points. It's like this trying to be in 3 dimension, which is not. Yeah, it's this line here. Let's just see where I messed up. I had EX, EY. It was equal. Oh, I was close. It was it. Where did I mess up? It was correct what I did earlier. Plus this guy. EY. Oh, I should have written this as one array. What did I do? np.array. That's what I've written. Oh, I just forget. Oh, I want RE. I've written array. I think this would have worked, wouldn't it? Yes. Yeah. Oh, just the one mistake. Perfect. But this is it. Yes, I made it from scratch. Very good. Okay. Perfect. Very good. This is exactly what we want. So you can imagine the rings here are here because this is the XY plane. And this is how the contribution would look. Like we are here and it will affect us like this. And if I did this in the in terms of the XY plane, we would get the exact same. But now we have this in the XZ plane. But this is just perfect. Very good. Okay. Now we can continue to linear algebra. So let's go back to our iPad here. Okay, now a new chapter on linear algebra. This is coordinate systems. This one is very interesting. So let's start. So let's say we have some vector space V. Why do you want to specify a basis for that vector space? The reason being is that we impose a coordinate system for that vector space by our basis. Our basis serves as, we will see because we will look at all kinds of coordinate systems, but our basis will serve like we're used to with the standard basis vectors, right? We are used to having imposed the x and y coordinates, right? So we have the standard E1 in terms of x and E2 in terms of y, right? You will see it more clearly in the examples what I mean. So if B then contains n number of vectors or space, so B has n vectors, the space, of course, it will act as it's in R of n, right? But if V is already in Rn, this will then determine a new view of that coordinate system. And we often have this in physics. So let's say I have this guy right here. This is our normal x, y, z. I can of course do this. There's no reason why, if all of these are perpendicular, so x prime, y prime, or z prime, you could also have a transformation. You're still in, let's say you're in R3, or let's say R2 then. And then, or your lines are like this because we are just in the standard basis. But let's say you had some kind of skewness, which means that, let's say maybe you double the y or double the x, then your coordinate system may look more like this, and you will see it. You will see it in one of the examples because they don't need to be 1, 0 and 0, 1. They could equally be 1, 0 and maybe 1, 2, for example. Those are just different bases. So for every y, there's 2 of x here, right? You can see that. Okay, so that is the motivation here. We are also going to have a theorem, and that is the unique representation theorem. So we're going to let B some kind of basis for vector space V. So B is this basis here, and it's the basis, which means that the span span of B covers V, so that's the basis for V. Then for each x in V, so for every x in V, then it will just be a unique set of scalars in order to represent. You could say this will actually be our coordinates, but there will be a unique set of coordinates in order to represent that vector. So what I'm saying is that this equation here can only be represented for only a unique set of coordinates, or you could say constants, right? What I'm trying to say is, like we're used to, if I have some kind of coordinate system, if I have this vector right here, if I used the standard basis vectors, these two guys, I can only represent this vector one way. There's no other way, right? If I wanted, let's say I want to represent this vector, let's say I had to go 1 point, 2 point, and then 3. Let's say this was 3 steps here, and this was 1, 2, 3, 4. There's no other way than 3, 4, right? I need C1 to be 3, and I need C2 to be 4 in order to represent X here if this guy is X, right? There's only one single way. And that is also if you have other types of bases, right? Because they are linearly independent. That's the whole thing. Okay. Now we can do a proof of that theorem. It's a pretty simple proof. So now we specify that x is this, but let's say we picked some other x. And it was, no, let's say we picked the same x, but we try to represent it with different constants. Or no, that's not the correct argument. Let's say we picked the same x, and we're trying to say that we have different constants. We don't know yet. We just say that we have picked the same x. Should we just call this d1? But it's still b1 because those are the bases. That's up to dn and bn. And then x minus x is of course 0. And then, of course, 0. And then you, of course, get c1 minus d1. And then b1 plus up to c n minus dn. And then bn. And now, of course, since b1 up to bn are linearly independent, that means that, of course, it's only the trivial solution, which means that this has to be 0. So c1 has to be equal to d1, or more specific, c of, let's say, j has to be equal to dj for every j between 1 and then, of course, up to n, right? So you could say j, like that. Okay, so that should make it clear that, of course, this vector can only be represented one way, and that's a unique way, right? Okay, so let's move on, right? What are the b coordinates of x, or the coordinates of x relative to the basis? Use an example. Ah, yeah. So, like I said, this will be the coordinates, and we actually have a name for it. We say that it's the coordinate relative to your basis, right? So if I have, let's say I have 2, 1 and 0, 1 as my two bases, then I would say that, let's see, I would say that the coordinates, right? In order to move in this coordinate system here, if I had, let's say, 3 and then 4, I would say that my coordinates are 3 and 4. We're actually used to it, right? When we're in physics and we write x and y, we usually write 3 and 4 like this. This means the same thing, but we just have a different coordinate system. Instead of 1, 0, we have 2, 1, right? But it's still the same thing, right? So now, instead of with respect to the standard basis, it's now respect to this basis right here. So we are saying now, in this case, that x, and we are actually writing it like this. So x with respect to or relative to the basis, the coordinate of x now is 3, 4. That's what we're saying, right? I'm going to do an example and demonstrate. So let's see. It was, where is this? I don't want to lose this one. I don't want to lose, yeah, we can just go here, like that. Linear algebra, okay. We are on 4, 4. Matrix, no, not that. It should be, there you go, 4, 4. Yes, here's the example, okay. So, consider a basis B. So consider a basis B, that's just equal to B1 and B2. And it's for R2, where B1 is equal to 1, 0. Okay, so B1 is equal to 1, 0. And then B2, no wonder I was writing that all the time. 1, 2. And then suppose that x in R2 has the coordinate vector, so x relative to our basis is equal to -2, 3, like that. Find x. So find x in the standard basis, that's what they're asking. So this is, you can write this multiple ways, it's actually pretty interesting. So I could state multiple things there. That's very cool. I could actually state that what we have is that this is our machine, 1, 0, 1, 2. And if I run -2, if I run -2 and 3 through our machine, I should get some kind of x1 and x2. Shouldn't that be it? Yeah, I should get some kind of, that's our machine, or is it, no, it's the opposite, isn't it? Let's see. I have -2 and 3. That's that guy. Let's think just for a second. Is it x? Yeah. Oh yeah, that I can write release. So if I run C1 and Sin2 or coordinates, I should get, yeah, the output of a machine is that guy right there. That should be correct, right? And this is pretty interesting because this literally transform or coordinates. No. Oh, how am I? What am I thinking now? Let's see. I have -2 and 3. If I put -2 in front of B1 and B2, I will get the answer, right? Isn't that it? What was the? Let's see. PB, what does it? Let's see, which way should I do this? XB or coordinates. So if I took -2 and 3, I need to solve for x. Let's think. I know how to solve this, I just want that nice representation, which I liked. I C1 and C2. No, actually, that's not C1 and C2. That will make 0 sense. What I actually run through there, I have -2 and 3. That's correct. I'm pretty certain that's correct. So -2 and 3 is what I have. Yeah. Yeah. So I would, let's see. -2. Then I would have 3 -2. I don't think that's the right way to do it. Let's see, I get -2 there. So we have XB. Let's see. It should be the solution, right? I should run through that guy, shouldn't I? I can actually write both ways. Okay. I have this guy there. Let's see. I could state, there's multiple ways I could state this. Let's say if we did -2, 3, right? That's the machine. This is -2, 3, right? And then I should get x1 and x2. Yes, I think that should be much more neat. Because then I could state that there's some matrix PB, which is equal to B1 and B2, right? Yes. That should be pretty clear. And then I could state that PB, do I want equal? I want PB. Why I wouldn't want X there, that wouldn't make any sense. Times. Oh, what did I do then? Okay. Okay, let's get back to this in a second. Let's just solve the one above and see if we can make something out of it. Okay. So in order to solve this guy, you could either augment this matrix, because as you will see, if I did this, this means by the invertible theorem that it has a solution, right? There's an invertible here, right? So this means that that equation right there, if I represented, if I had PB equal to B1 and then B2, that matrix there, and what we're saying, I'm trying to solve for X, shouldn't it? I think, oh, why am I forgetting this? Is it PB times X is equal to 0? No, that wouldn't make any sense. No, I don't think that was the right idea. I would have stated that either PB and that is X, shouldn't it? Okay, let's see. Let's try. So we have X in terms of basis. That should be X. And if I multiply it on the left side, PB minus, ooh, that should be it. It's the other way around, isn't it? Isn't that it? So I have X times X. That should be X and then B, right? And if I multiply by the invertible theorem, I get X, and then I get PB minus 1, and then X. Just like that. Yeah, okay, that's how I wanted this. Yeah, now you can see what I just written here. The solution to X is the same as here. You see, the solution is just to invert that matrix there, right? So if I inverted this matrix here, I just have 1 here, and I invert it, I will actually find X, as you see, right? So I just have to invert X, and with that guy, is that correct? Oh, that also seems weird. Okay, let me just look for a single second. What did I do here? It was this nice writing where I messed up. I didn't write it here? Why didn't I write it here? Here you go. That is what I wanted to look at. So I had X. Yeah, okay, so this was for later. Oh, no wonder why I messed up. Oh, I didn't even want to do that. Ah, of course. You moron. I should just solve this straight ahead. I was one step ahead of myself. God damn. Okay, what we actually want to just example one. I'm sorry. God damn. Okay, yeah. Okay, so let's restart again with that definition and then go to example. Okay, so definition. Okay, so the B, right? The B we had, we actually have a definition where we say that those coordinates, those B coordinates, they are the coordinates of X relative to the basis B, right? So like I said again, this could be 0, 1, and this could be 2, 1, and then we could have C1 and C2, which are those coordinates, right? And what we're actually doing then, because this will be X now, suddenly, right? So we have some kind of mapping here, right? So what we can also state is that we can also do this both ways, but we can also state by definition that X, the mapping from X and going to these XB, the coordinates with respect to the basis, is determined by the basis, right? That's what we want. Okay, now we can go to example one. Ah, you moron. Okay, so now let's go again. I can just copy this out so I don't have to mess around like I did. Yeah. Oh my god, is it possible, right? Okay, so consider a basis for R2 where B1 is equal to this and B2 is equal to this. Suppose an X in R2 has the coordinate vector X to B is minus 2 and then 3. And then find X, right? Okay, so we need to just find X. And what did I have? Yeah, so that coordinate X B, just like that, is equal to minus 2, 3. I have to also just give me 2 seconds. Okay, I just have to stop. There was something there, but it's all right. Okay, so I have XB there. Okay, and those are our coordinates, right? So again, X now, it's just minus 2, because that's one coordinate. And with respect to the basis, so 1, 0. And then we have the second coordinate, which is just 3. And with respect to the basis 1, 2. It's the same as having the unit vectors 1, 0 and 0, 1. But now we just have different bases. And this will, of course, just be minus 2 plus 1, right? No, minus 2 plus 3, so that's just 1. And then, of course, just 6. So 1 and 6. So now we did a mapping from XB and to X here. Cool. Very cool. Okay, that was example 1. Yeah, that's 1, 6. All right, and here the entries are this relative to standard basis, and that's just, of course, 1 times the unit vector 1, 0, and 6 times the unit vector 0, 1. So you see how this is it's the same thing, but we just have different representation, right? There's maybe a coordinate system that's more skewed than the one that we're used to, right? So you can see now in this graphical interpretation, and here you can see it, right? So here in our example, this was in terms of those bases that we had, but this is the standard basis. These are our bases, right? And it's skewed like this. This example also shows a bit about what this is about. Now the example 4 where I messed up. This was what I wanted. Okay, example 4. So now let B1 is equal to 2 and 1, right? Then we have B2, which is equal to minus 1 and 1. And then we have X, which is just equal to 4 and 5. And now the basis B is then B1 and of course B2, right? And now we want to find the coordinate vector xb of x relative to b. That was what I was thinking about. I was thinking so hard because it was just all wrong. I was thinking so hard. Now this of course makes sense. Earlier it didn't make sense at all. Okay, so of course now we can add this as a matrix, right? Now I have 2, 1, minus 1 and 1. And what do we want? We want to run C1. There's some C1 and C2. If I run those coordinates through that machine, I will get 4 and 5. I was thinking so hard about this earlier. Yeah, so that is the representation here. So we have multiple ways that we can do this. Of course, I could represent this guy as, let's say, PB, like I tried to do earlier. So, which means I can write this as P, B, and then we have C1 and C2. So we have X like that, and then with respect to that basis, right? And that's equal to, of course, X, now by the invertible matrix theorem, because as you see from here, I can, of course, if I did the inverse here, I would just get x of b, which we are looking for, which our x with respect to b, what we're looking for is just the inverse of pb, right? And then just run x through that machine, and then we'll get the answer. Okay, so one solution then is of course 2, 1, minus 1, 1, and then you can just use this augmented matrix in order to invert it, right? That's just one solution. But now, as you also see, we can also just extend this guy in order to get the solution. So I could also say 2, which is much simpler. I prefer to do it this way. 2 minus 1 and 1 is just a matrix equation, where C1 and C2 would go in here, right? And then we just can extend this by the solution, 4 and 5. Okay? So now what I can do, I take 1 and just remove. Minus 2, that's 0. Minus 2, that's minus 3. Minus 2, that's minus 10. And of course, minus 6. Just like that. Okay, we can of course flip that guy. So that's just 1, 1, 5. Then I can divide by minus 3. So I get 1, 0. I get 1. And of course 2. Right? And then again, we can just 0, 1, 2. 1, minus 1, that's 0, minus 1, and that's just 3. And you can see, of course, that C1 should be equal to 3 and C2 should be equal to 2. And there's, of course, our solution, right? You can also test this if you run 3 and 2 through that machine. So 3, if I ran 3, I will get 3, and then of course I will get 6, minus 2, which is 4. Then I will get 3 and 2, and that's 5. So you see that's also correct. Perfect. So our xb like that is equal to 3 and 2. And that is the coordinates with respect to our basis, right? Perfect. Very, very good, right? I think this was a very nice way to see it. We could also go back. So this is actually our some kind of Rn. In our case, this is R2. So this is a one-to-one relationship from going from one R2 to another R2. And we can, of course, go back, right? Okay, my time is nearly up. Can I do some tasks? I actually want to do some tasks, but we are very close to finish. Let's see, I had these first. Let's see if we can do them. Some of them quick. 3, 12, and 36. Right, okay. So we have 3, 12, and 36. Okay, determine if they are bases for our tree. and which are not, and which one are linearly dependent span R3. Okay, you can just add them together, into one matrix, all of these three. And if you get the pivot for all of them, that's of course, they will form a basis and span R3. And it turns out that only 2 of them are independent, and that third one, I think this one is not independent. You can just did what we just did here, same thing. And again, the pivots will determine. I think the last one, this guy had 3 variables, so only these 2 are independent. So these 3 together are not independent, and they of course don't form a basis, and they of course don't then span R3. They're not enough, right? Okay, the next was 12. So let's see, task 12. Find a basis for a set of vectors in R2 on the line y is equal to 5x. So you can use that. There's a lot of ways of doing this. You can just see it, but you can also say that y minus 5x is equal to 0. And now you suddenly have a null space. You suddenly now have a, where a is just 1 minus 5, like that. Yeah, a is 1 and then minus 5 like that, and you get that those 3 variables. But you can also clearly see, if I took outside, if I had this ax is equal to 0, you need that 3 variable principle. So if I set x outside, right, how can I get x? That's just 1, right? But how can I get y? I need to multiply 5 by x. So of course the solution is 1, 5. That should be correct. Okay. That was 12. What was the next one? Can we do this quick? Next one is 36 and 26. I don't know why they write it like that, but 26. A base is a linearly independent set that is as large as possible. True. It's just a true or false, right? Why? Because for R2, right, I need 2 vectors. I need 2 vectors in order to span as efficient as possible. That's the biggest in the linearly independent set. If I have 3 vectors, I know it's impossible to have 3 vectors and be linearly independent because you only need 2 for 2 dimensions, right? So a base is a linearly independent set as large as possible, yeah, or as efficient as possible, that you can also say. Okay. And we also have 36. What was 36? In the vector space of real valued function, find a basis for the subspace spanned by these. Yeah, pretty easy. I can take 10 times sine t, for example, but I can't represent sine t with sine 2t, right? Because 10 times sine t, it's not sine 2t. It's not the same thing. But sine 2t is, of course, the same as 2 times sine t cosine t, which means that if I divide this guy by 2, I get this guy. So all I need is either these 2 or this guy and this guy. And that's our basis. Okay. Perfect. I have some more tasks, but we can leave them to next time, right? Because now it's getting late. Okay. It was a stupid struggle, but it's all right. That's what happens. And I'll see you tomorrow.